So we are going to wrap up our look at calculus for the year with a quick preview of some of the university content you're going to see. Now, with integrals, we have just barely scratched the surface of what we can do with those. So just know there's a lot more coming. If you're going to the U of A and take, say, 114, 115, 214, and 215, this is the mainstream math and science version of calculus. If you're engineering, they squeeze these 4 courses down into 3 courses by omitting some of the proofs. Engineers will deny that. They say, no, we still see lots of proofs. They do see far more proofs than you're used to coming out of high school. But speaking as someone who took both engineering and non-engineering versions of the math courses, someone who looked at the notes in the textbook, yeah, more proofs than you're used to. Still, not as many proofs as the mainstream math. And if you're a math major and taking the 117, 118, that's real analysis rather than calculus, it's virtually all proofs, nothing else. So yeah, a lot of proofs, not as many proofs. That's how they squeeze it in. But if you're doing that, you're also going to see a few other things with derivatives. And there are 2 other key kinds of derivatives that haven't been covered. And since those are really the only 2 kinds of derivatives you can take that we haven't covered, we might as well do it here. So the first is the partial derivative. So we have seen before that if you take, say, the derivative of f with respect to x, well, then you end up with that derivative of f times the derivative of the inside with the chain rule, right? If we just have f, it comes out like this. If we've got the derivative of f of u of x, then, yeah, we'll have that chain rule bit. Sorry. So the f primed of u of x times u primed of x. Well, what about partial derivatives? Right. Let's say we also had a function that depends on x and y and z. Now, generally speaking, if you take the derivative with respect to x, you'll have all the derivatives you expect with the x terms there. You'll also have terms where you take the derivative of y with respect to x and the derivative of z with respect to x. So if it depends on multiple variables, you end up having to apply the chain rule to each of them. The partial derivative eliminates that. So if our f of x, y, and z was just the product of x and y and z, then the derivative, or the full derivative of f with respect to x is going to be yz plus x derivative of y with respect to z times z plus x, y, and the derivative of z with respect to x. And I think I said derivative of y with respect to z, I meant with respect to x. This is the full derivative with all the chain and product rules we're used to. The partial derivative, with these symbols that we pronounce di, so instead of df by dx, it's dif dx, pronounced di, just the di, which I should have, sorry, I forgot where my head was going to be positioned in this video. That's what's under me down here. So that dif dx, in this case, is just what you get when you take the derivative with respect to x and pretend everything else is constant. So it is just that simple, intuitive yx. So that makes the partial derivatives easier to deal with because that fits your instincts. If you have any issues, it's usually forgetting whether to use the partial or full derivative in any given case. The other derivative we can get is a vector derivative, because some of our functions are themselves vectors. So to do that, we have to have the 2 vector products. Now the vector product is when you multiply 2 vectors together. this dot product is x component times x component, y component times y component, plus z component times z component. So if this nabla, this upside down triangle, is a vector that is the derivative with respect to x in the x coordinate, derivative with respect to y in the y, and derivative with respect to z in the z, then this dot product is df dx plus df dy plus df dz. This is what is known as the divergence. It measures how much things come out from a central piece. If you're doing electricity and magnetism, you will notice that this is the one that is the shape of the electric field. Whereas the next one, the curl, is much more complicated. Generally speaking, if you have the cross product of A and B, you end up with a third vector perpendicular to both A and B. So this is how you multiply two vectors together and get a vector out of it. Now the way that works is a little complex, but if you have the cross product of F with this, you have what they call the curl. It's a measure for how much things close in on themselves. In physics, it's like the magnetic field. But this, as your x component, will be the y derivative of the z component of x minus the z derivative, of the y component of x. So this is the x coordinate, and then we have a little bit of a cycle where the signs change each time. So the y coordinate of this, we do have that cycle. So yes, it's the y the derivative, and then the z of the derivative. With this one, we'll take the second one first, so it's the z derivative minus the x derivative, which means that's fx, and that's fz. And then our z component is going to be back to alphabetical order, so it'll be the x derivative minus the y derivative of fy minus fx. So that is a very, very nutshelled version of everything you could possibly do with derivatives that we haven't already covered, at least until you get into the fractional calculus. We've talked about, the first derivative and the second derivative. If you put the numbers in brackets up here, that tells you how many times you've taken the derivative. Believe it or not, it is entirely possible to have fractional derivatives, or even irrational derivatives. But that is way beyond the scope of high school, and probably even most undergraduate math programs. Doesn't mean it doesn't exist.